Okay, so in this quick video, I will be explaining the tensile test to you. So what you have is animation that is showing you the typical setup. So this over here is your test piece and then it is held between two grippers. One of the grippers has the load cells, generally it's the top one, and generally the bottom one is fixed, but you can have other arrangements as well, especially with a UTM. You can have both the frames moving as well, but in many cases you'll have one of the sides fixed and the load being applied from the other side. So this over here represents an extensometer, and this extensometer essentially records the change in length between these 2 points on which it is attached to the test specimen. Now, as we start applying the load, essentially we will be able to obtain what we call as a load displacement plot, and that will allow us to study the behavior of the material. Now, the problem with the load displacement plot is that if you change the area of the specimen, you end up with values that will change, so that load and deformation response will change. Because we want to express the whole behavior of the material independent of its geometry, therefore we use the concept of stresses and strains. And instead of simply using the load, we use load per unit area, which is your stress, and with the assumption that the intensity of the force distribution is actually uniform, so we can use the entire cross-sectional area of the specimen. And we also use strain, which is change in length given by this extensometer divided by this original length, which is over here. So we use that to find out the strain. So let's now see this virtual test in progress. So that's what has been explained here, that more useful to that load deformation plot is the stress strain plot. So let's see. So in this video we will be looking into this virtual test. First you'll be shown the load displacement curve, and then we will show you the stress strain plot. This is going to be a typical behavior of materials such as aluminum or heat-treated steels. So, as explained over here, generally the lower grip remains stationary while the upper grip moves upward, and thus creating tension in the specimen. So the specimen is being pulled. Okay, and you measure the load from here, from the top. Now, different types of grips are used. You can have flat grips, you can have round grips, you can have wedge grips. Again, that depends on the type of the specimen. Most metallic specimens, and now the shape of the specimen is actually dictated by the testing standard that is being used, and I've already covered in my earlier video how you can obtain some of those testing standards from the library. So have a look at that, and essentially all that you need to do is you need to pull this, you need to make sure that you have got a uniform stress distribution within your specimen. So if the specimen shape is flat, you'll generally use flat grips or V-shaped wedge pairs. Okay, so that's what we generally use. But for metallic specimens like the ones that you will be using for your test, then you will be using round grips with the grooves, as shown by your technical instructor in the photos given to you about the specimen. And that's the type of the specimen that I'm just talking about. So this is specimen with some upset threads. So this will fit in on this portion and one at the bottom, and then it will be pulled. Okay. Now, an important point is that the rod diameter at the ends is larger than the specimen diameter. So the presence of threads therefore does not reduce the strength of the specimen in this case, and careful consideration has to be taken while machining these, so that the stress concentration because of these threads is not so large that it actually starts breaking closer to these grips. It's a requirement of this test that the stress state, or the force intensity distribution as we call it, is uniform throughout. Now, a bit more about the extensometer. So you can see here, this is clamped onto the specimen using these knife edges, and that allows you to precisely measure the movement as the specimen stretches, and that then allows you to measure the change in the length. The original length is called as the gauge length. So on your data sheet, it will be written as your initial length or the gauge length, and then using that original length and dividing it with the change in length, you'll be able to find out the strains. Extensometers are generally capable of very precise measurements. Elongations as small as 0.0001 of an inch or 0.002 millimeters are possible, and they are available in a range of gauge lengths, with most common models ranging from 0.3 to 2 inches, that is from 8 mm to 100 mm. These days, we often also use video extensometers instead of these ones with the physical gauge. The principle of working of these gauges is actually change of resistance. So essentially, when this opens up, it results in the change in the resistance because there's a wire inside. So that wire gets stretched, and that is the change in the resistance of that wire is calibrated, and based on that change in resistance measurement, you then measure how much length has changed. Now, several measurements are made before, during, and after the test. Before the test, the cross-sectional area of the specimen must be determined. The area will be used with the force data to compute the normal stress. The gauge length of the extensometer should be noted, and the normal strain will be computed from the specimen deformation, that is the axial elongation, and the gauge length, as I just explained. Now, during the test, the force applied to the specimen is recorded regularly, so it's continuously recorded. There will be a preset time depending on the machine's capability. It can be set to every second, or even much less than a second. Again, depends on your data capture device. The elongation in the specimen between the extensometer knife is also measured continually at the same time. After the specimen has broken, the area of the cross-section at the fracture location is measured. The reduction in area between the area of the fracture and the original cross-sectional area divided by the original cross-sectional area provides one measure of the ductility. So essentially, it's telling you that how much the area reduction has happened. So that's again one way of looking at ductility. So, but overall, the term ductility describes the amount of strain the material can withstand before fracturing, and that can be seen by the stress strain curve itself. So we'll look into that as well when we actually show the final curve. So let's now look at this virtual tensile test for an aluminum alloy specimen. The load and deformation data will be plotted in real time. So if you click the forward button, it will start your virtual test. So you can see the load is increasing as the specimen is being pulled up. And you can see the plot initially is very linear, but now it has started to curve. And the deformation is increasing much faster now. You can see the elongation is increasing much faster. The load is then starting to drop, but the specimen is still elongating, and you can now see some reduction in the area as well. That resulted in the neck and then final fracture. So these are the typical features that you see before the final specimen failure or the bang. And this is a typical load deformation plot. Again, more of the machines use the SI system. On this, we have shown it in the pounds-inch system. Both system of units are still in use. Now, let's look at the tension test again, but this time we will explore another interesting characteristic of the material. And what we'll do is we'll halfway through stop the test and we'll unload the specimen and observe the response. So it's again loading, and if you see, the plot is initially linear, okay, and just when it reaches this point, when it becomes slightly non-linear, let's pause it and unload the specimen. Okay, now the load at this point is 13,230 pounds, And if I now move forward and unload the specimen, meaning that I reduce the load or remove the load, it will start going back. But it does not follow the original plot. Rather, it actually falls down at this at some value of strain. Okay, so in this case, of course, we are plotting the deformation. So it goes down at this 0.0799 of inch. So that's a permanent deformation that is there, and this is basically now a plastic deformation that has happened. Okay, if we had now again resume the loading, it will follow the line, and so it will keep following the line. Sorry, it will keep following the slope of that black line, but it will move up the same line on which it came. And this time it will not start curving at this point at which it originally did, that is around 11,860, where it started becomes non-linear. It will actually keep its linear behavior to this top point over here. So you can see, and then it actually unloads, it becomes non-linear at around 13,230 pounds. So again, the specimen starts to neck down, and the area of the specimen is at narrowest. Then it starts to neck down, and then it actually fractures at this particular load. Now, if you see this phenomena over here, which had just happened, that you have effectively increased the point at which the specimen actually goes into yield. This is called as strain hardening. So if you give the specimen a bit of permanent deformation, next time when you load it, the yield point has actually shifted. And that's something which we use in the manufacturing or for work hardening the material. So we are effectively increasing the yield point of the material to achieve this. Now, the unload behavior seen here is very useful characteristic, particularly for metals, and that's what I've said. One technique for increasing the strength of material is the process of stretching and relaxing, called as work hardening, and that utilizes this. Okay, now from this load displacement plot, we can obtain the stress strain diagram. And to construct a stress strain diagram for each data point, now remember we have to do that for each data point, divide the specimen elongation data by the extensometer's gauge length, and you obtain the normal strain. You divide the load data, which is the force, by initial specimen cross-sectional area to obtain your normal stress, and then you plot the strain on the horizontal axis and stress on the vertical axis. Now, if you see, in comparison to this one, I've shown you the stress strain plot over here as well. Again, this is being shown in the units of PSIs, although we normally prefer using megapascals unit these days for stress. So this shows you the basic stress strain plot and how to obtain them at some of the features. I will have another video in which I will actually go through even more details of the stress strain plot and the different regions on that stress strain plot. So thank you very much.